Hello and good day. Welcome back to our class. This is teacher Onin Guzman and our topic for today is solving rational inequalities for general mathematics. So before we solve rational inequalities, let's recall first the properties of inequalities. So we have the sense of an inequality is not changed if both members are increased or decreased by the same number. Also, the sense of an inequality is not changed if both members are multiplied or divided by the same positive number. On the other hand, the sense of an inequality is reversed if both members are multiplied or divided by the same negative number. Having said with this, we can move on to solving rational equalities or inequalities. So, first is rewrite the inequality with zeros on one side. Next also is rewrite the inequality as a single rational expression. Notice that the steps 1 and 2 is not applicable on some occasions. Third is determine the boundaries. Then we will use test points. And finally, we have write the solution set. So let's talk about the first case, meaning to say the zero on one side. So we have here, in order to solve the inequality x minus 1 all over x plus is greater than 0, so the first step is to determine the boundaries. So to determine the boundaries, we will let x minus 1, the numerator, is equal to 0. So x is equal to 1. So this is the function is 0. On the other hand, x plus 3 equals 0. It means this is the denominator, which x is equal to negative 3. It makes the function undefined. So since we know already the boundaries, so on our number line, we will take negative 3 as well as positive 1. Since this is greater than, so we will have actually half line. Next, we will use the test points. So having said with the test points, it means that we will choose numbers beyond negative 3, in between negative 3 and positive 1, and beyond positive 1. So, say for instance, if we will let x is equal to negative 4. So this is to the left of negative 3. So again, with our original inequality, substitute the value of x. So we have negative 4 minus 1 all over negative 4 plus 3. Is it greater than 0? So since negative 5 over negative 1, or we can say that 5 is equal to 0, is true. So therefore, we will mark this one as correct region. On the other hand, if we will choose between from negative 3 to positive 1, say for instance, I'll choose 0. So we have this expression, then substitute x by 0. So we have now 0 minus 1 all over 0 plus 3. So we have negative 1/3. Is it greater than 0? Obviously, this is false. So meaning to say this region is not included in the inequality. Next, if we will go beyond positive 1, say for instance x is equal to 2. So again, use the expression, original expression, or inequality. So I have here plus 2 minus 1 all over 2 plus 3. So in short, this 1/5 is greater than 0. So therefore, this is actually true. Now, since I know already my boundaries as well as the area covered inside or within the inequality, I can say that here. So I can write now the solution set. It means that if I'll use this, okay, interval notation, from negative infinity, as you can see, from negative 3, meaning to say excluding negative 3, union, since I will not use this region, union from positive 1 to positive infinity. Or I can rewrite this one as x, such that x is an element of real number, such that x is less than negative 3, or x is greater than positive 1. Let's move on to the second case. So that's why we will have renaming the rational expression by the least common denominator. Say for instance, I have inequality 2x all over x plus 1 minus 1 is greater than or equal to 0. So the first thing that I'll do is rename the inequality as a single rational expression. To do this, I'll consider the LCD x plus 1. So, since I know the LCD is x plus 1, I'll rename the rational expression. So, to do that, let's review. So, x plus 1 divided by x plus 1 times 2x is equal to 2x. On the other hand, the denominator of negative 1 is actually 1. So, x plus 1 divided by 1, okay, times negative 1 is actually negative 1 times x plus 1. So, again, it can be simplified as, okay, this expression because I can combine the same denominators. In numerators, I'll distribute negative 1 times x is negative x. Negative 1 times positive 1 is negative 1. Then, simplify. I can have 2x minus x is equal to x minus 1 all over x plus 1 is greater than or equal to 0. Now, I know this already since the derived, okay, inequality is equal to x minus 1 all over x plus 1 greater than or equal to 0 as a single rational expression. The next step is determine the boundaries. So, again, if the numerator is equal to 0, so x is equal to 1, so the function is equal to 0. On the other hand, if x plus 1 equals 0, it means the function undefined. So therefore, on the number line, I'll use the whole. Okay, this meaning to say I'll include 1. On the other one, I'll exclude negative 1. So these are my boundaries now. So I would like to determine which area is included in the inequality. So, step 3 is use the test points. So I'll go beyond negative 1, say for instance negative 2. So I'll use the derived rational expression. So therefore, negative 2 minus 1 all over negative 2 plus 1 is greater than or equal to 0. So we can say that 3 is greater than or equal to 0, and this is actually true. So meaning to say this area is included in the inequality. On the other hand, if x is equal to 0, because this is between from negative 1 to 0, and that is the easiest value that I can use, so we can say that negative 1 all over 1 or negative 1 is greater than or equal to 0. And of course, this is false. So meaning to say this area is not included in the inequality. And finally, if I use x is equal to 2 beyond positive 1, so this expression is the same as 2 minus 1 all over 2 plus 1. Is it greater than or equal to 0? So we can say that 1/3 is greater than or equal to 0, which is true. Take note that I can include here 1. So on my solution set, I can say that from negative infinity until negative 1. So this is parenthesis, open and close parenthesis, union. So I use here bracket because I'll include 1, okay, until positive infinity. Or I can use the interval notation such that x is an element of real number such that x is less than negative 1 or x is greater than or equal to positive 1. The third case. So that is rational expressions on both sides of the inequalities. So say for instance we have inequality 3 all over x minus 2 is less than 1 all over x. So the first thing that we will do is rewrite the inequality with 0 on one side. So that is why we subtract both sides of the equation by 1 minus x. So we will come up with expression or inequality 3 all over x minus 2 minus 1 over x is less than 0. The next thing that we will do is rewrite the inequality as a single rational expression. Note that the LCD is x minus 2 times x. So we rename both sides of the equation. So again, so the LCD is x times x minus 2. So we have here x times x minus 2 divided by x minus 2 So that is equal to x times 3, the numerator, minus this expression. So again, so x times x minus 2 divided by x is equal to x minus 2 times 1. So we have here, simplifying it further. So distribute, since here we will distribute the negative, but before that, we can combine because we have the same denominator now. So I have here 3 times x is 3x. Distribute negative 1, so I have negative x. The negative 1 times negative 2 is equal to positive 2. Simplifying it further, I have 3x minus 2 plus 2 all over x times x minus 2 is less than 0. Or I can say this is equal to 2x plus 2 all over x times x minus 2. So, but I can factor out the common factor, which is 2. So I have here 2 times x plus 1 all over x times x minus 2 is less than 0. So since we can say that the expression or the inequality 3 all over x minus 2 is less than 1 over x can be renamed as 2 times x plus 1 all over x times x minus 2 is less than 0, we can now determine the boundaries. However, if we will observe the numerator, so since this is 2 is constant, I can only write here 2x plus 2 can be renamed as 2 times x plus 1. So I'll just consider x plus 1 is equal to 0. So if x is equal to negative 1, so the function is 0. On the other hand, since I have here x times x minus 2 using the 0 property, so I can say that x is equal to 2 or x is equal to 0, so the function is undefined. So since I know the boundaries now, so on my number line, I'll use these three boundaries. I have negative 1, 0, and positive 2. So therefore, I'll use test points. So how many regions do I have here? So let's count. So this is 1, 2, 3, and 4. So meaning to say I'll use 4 test points. So if x is equal to negative 2, using the derived formula or derived inequality, so I can have this expression as 2 times negative 1 times negative 2 times negative 4. So we can say that this is true. Okay? On the other hand, if x is, say for instance, negative zero point 0.5, so that is between negative 1 and 0. So using this expression or this inequality, so substitute the value of x is equal to negative 5. So I'll come up with 2 times zero point 0.5 times negative zero point 0.5 times negative 2.5. So therefore, this is 2 fifths is less than 0. And this is actually false. Okay? So again, this is true. This is false. Let's move on to this area now between 0 and positive 2. If x is equal to 1, so look at this one. So we have 2 times, okay, simply substitute the value of x is equal to 1. So I found out that, okay, this expression or this inequality, negative 4 is less than 0 if x is equal to 1, which is true. On the other hand, if x is equal to 3, so I'll go beyond positive 2, going to positive infinity. So this expression will result to 2 times 4 all over 3 times 1 is less than 0. So this is actually false. So again, this region is true. So this is included, this is not included, this is included, and this is not included. So therefore, my solution set now, okay, after I graph this, look at this one. So if I'll write the solution set, so this is from negative infinity to negative 1, union from 0 to, okay, positive 2. Or I can rewrite this one interval as x such that x is less than negative 1 or x is greater than 0 but less than 2. So that ends our discussion on solving rational inequalities. Again, this is teacher Onan Guzman. Do not forget to subscribe to my channel so that you will be notified about my new videos. Thank you.